speaker, Thomas.
Yep. So thank you very much. So just a moment.
Just a comment on the time, considering that we are a little bit late. We have a margin. I mean, we had 15 minutes margin at the end. So use your 30 minutes, Thomas. That's okay.
Okay, fine. Thank you very much. So in my presentation, I want to demonstrate how a dynamic fault injection for SystemC AMS can be used for quantitative safety verification. So imagine there is a design under development, for example, a battery management system as part of a safety critical energy storage item. And such a system can include, for example, analog hierarchical battery models, a chain of monitoring balancing ICs as a mixed signal, up to a controller model, which includes also management software, which is running there. Beside that, also some sensor models are available for temperature as a temperature sensor for the battery package, and also a current sensor for the load, and also in order to provide a balancing functionality or the balancing network. The load is created by a driving cycle as a kind of load current. A simulation result can look like that for a nominal simulation, so fault simulation based on this driving cycle. Here you can see, for example, the battery voltage levels for each of the cells in such a kind of battery packages. And these voltages are depend only on the state of charge of a related cell and also on the load current. And you can see we are, because it's a nominal simulation, no error was detected. So it's a faultless simulation. So, but when this such kind of system is under development and the functional verification could be finished, it's necessary also to make an investigations under fuzzy aspects of that kind of system. Especially it should be part of a safety critical item, especially in automotive systems. So, for example, and this investigation can be done, for example, by using FMEDA in order for determination of a diagnostic coverage of such kind of system. Here you can see a small snapshot of such a kind of FMEDA. You can see the component of such item is in that case a battery pack. It's relevant for the safety. It is clear when they are defined for such kind of component several failure modes. How often relate to the entire modes, failure modes that can be occur. The failure rate is defined if no safety mechanism is available. If a safety mechanism is available, it can be defined or calculated in failure mode coverage and depend on that single point and residual failure rates. So we want to demonstrate for one example for one of the failure mode how it can be look like to set up such kind of fault simulation. We use this under voltage condition. For that under voltage condition, there is a safety mechanism SM2 here available, and this is defined as a measure of the battery voltage. And if a drop occurs, safety relevant components should be connected to redundant battery. And for that, we want to calculate the failure mode coverage. In order to perform such investigation, we have to extend at first our system model. We create an example of a board net, which includes, beside non-safety critical loads like heating system, window lifter, lamps, and so on, also safety critical loads like airbag, ABC, ASB, and so on, and define a goal. Also, for example, we should check the assessment of the safety concepts, and that kind of safety concept should be to a continuous supply of a safety critical board net loads also under critical conditions. And if, for example, an under voltage fault condition occurs, that these components should be switched to a available backup voltage supply. And now the dynamic fault injection approach is used in order to provoke such kind of under voltage condition. And beside to check the pure functionality of a safety mechanism, which is detecting and reacting on this fault, we should also prove on time matrix in order to be compliant to the automotive standard ISO 26262. For example, should be part of this standard is also a definition of a fault-tolerant time interval, which defines after occurrence of a fault a time period for the fault detection and also the fault reaction time in order to come from the critical situation back to a safe state again. And this should happen before a possible hazard occurs. And this period between the fault occurrence and the possible hazard, this is so-called as a fault-tolerant time interval. So we should check with a simulation that this is fulfilled by the, or can be handled by the fault safety mechanism, and also under certain conditions. So it should be checked the influence on different situations, also to the coverage of a diagnostic coverage. So it can be detected in any case, this problem. So a scenario which could be derived from that would be, for example, we have a board net of a critical load. We have a test interval for safety application. And if a fault occurs, for example, the main battery is not able to supply anymore with components, how it is reacting the complete system, the safety mechanism on that. And this occurrence here is done by the fault injection approach. So the scenario is also suddenly the main battery cannot be supplied with safety critical loads anymore. Essential is also the provider of this critical of this item and safety relevant component defines a fault tolerant time interval. And now it has to be proven that the safety is able to bring the system in stability again, and this should be happen fast enough. But here it should be also checked in order that what is the influence of the occurrence time of a fault to the compared to the requirement what we defined. So that means when what is the coverage, diagnostic coverage, based on different time points where I inject the fault. So here, shortly, I want only to define the principle of a dynamic fault injection. Really roughly, because it was several times already published, so it's not focused here, but you need to know some really important things in order to understand the approach itself. So first of all, I want to define what happens during the execution of a SystemC simulation. This execution can be split in two phases. In the first is the so-called elaboration phase, where the DOT combined with a stimuli checker and so on. From that is created a module hierarchy in the memory. And in the second phase, this module hierarchy is simulated. How this DOT, what kind of DOT, and how it's parameterized, and also what kind of stimuli should be used, was already for a certain test case defined in the test description during the before the compile time. And now the approach for the dynamic fault injection looks like that. We extend this test description with a fault description. This fault description defines the definition where a fault should be occur in the design hierarchy, when it should occur, and what kind of fault should be occur. This is mainly what has to be described there. On the other side, we have a pre-built fault injection library, which includes our complete injection mechanism and also several predefined fault models. And now during the execution, so during the runtime of a certain test case, we use this elaboration phase in order to reconnect some connections inside the DOT in order to inject and vet these in the fault description defined faults. And in the second phase, this manipulated module hierarchy is simulated when. But this manipulation occurs only during the runtime in the memory, not in case of source code or something like that. The advantage what we are seeing here is the clear separation between the design of a DOT and a test description, because faults from our point of view should be only part of a test and not part of a design. So therefore also we have no DOT code change, which is not necessary in that by using that approach. And also for sure avoiding bugs due to insertion of test artifacts, for example. So come back to the battery management system. We extended our boardnet, our battery management system by this example boardnets, what I demonstrated some slides before. So we've seen here, we have a battery model, and now the safety concept requires a stable power supply for safety critical components, for systems and so on. And this provoke of this under voltage condition is now done during runtime, like is shown here. So we inject during the runtime, we reconnect the connections of battery cells and use instead an alternative voltage supply, like is shown here. But you have to know or to note this. What is shown here happens only during the runtime in the memory, not in no netlist is available, which looks like that. This is the important key point. Yeah, the safety mechanism itself is now part of a safety application which run on the ECU. So what we have to do now, or what we want to provide here, is make what I said, a fault which is injected, and we want to check is a hazard event can be prevented or not. We have a regularly diagnostic test time interval that is defined here, and in the time between two test points, the fault is occurred. Here you can see there is a fault diagnostic time interval, which is happens between the fault occurrence and when the fault is detected, but it's exactly happens here in the test point. And when we have here, for example, a simple example, a fixed fault reaction time interval. And therefore, in combination between these both time intervals, the fault detection time interval, and the fault reaction time interval, there's a fault handling time interval. And this should be shorter than a fault tolerant time interval. So, but in certain conditions, we will see later on, can happen that this this fault handling time interval is not shorter. For example, you can see here, if it's really early in the beginning of the diagnostic test time interval, the fault injected, when this fault detection time interval could be, for example, too long. And when and as a result, this fault handling time interval exceeds this fault tolerant time interval. So we have a hazardous event. So and this should be proven by the dynamic fault injection interval. So we have several injection points where we inject and want to estimate the diagnostic coverage at the end. So the fault description, what I described before, is also embedded into this structured generation flow. So we do not model this fault description as in source code by hand. It is integrated into the generation flow. So we have a safety concept. This is specified in the requirement management tool, beside also the functional specification. So it includes this description also the requirement for the fault simulation, which is mainly enough only to have to define only several things, what I said already, where a fault should be included, injected, when it should happen, and what kind of fault should be injected, which is mainly enough. But we have also optional things which can be additionally defined, for example, derivation function for an statistical analyst and so on. But this is too deep for now. So, and based on this description, what is made here, an automatic source code and test case generation is created and the regression is run. For the analysis itself, so it's several possibilities useful. One would be, for example, an definition as in so we want to define when this fault should be occur. The main approaches are define intervals, regularly intervals in between, for example, these test points, or it can be also defined in so-called bisection interval. But the more usual analysis, what is used is a Monte Carlo simulation, which is should be shown here. We have which defines also the parameter space, which should be investigated. For example, in our simple example here, this is only the diagnostic test time interval. So the inject of a fault happens at random time points between two test, or in between a test interval. And we want to estimate the diagnostic coverage from the ratio of the faults with which are able to prevent hazards compared to all of the injected faults. The advantage of that analysis is it gives the best efficiency for the many parameter spaces. So for sure, we have only a simple example. We only investigate one parameter space, the diagnostic test time interval, but it becomes really can also become very complex. For example, when you also have a variable reaction time interval and so on. So therefore it also can map whole parameter space. The disadvantages, but also on the other side, this is normally not sensible for one parameter space and required accuracy. But we want to take a look here in order to make it simple. Therefore, we only focusing on one parameter space. And Monte Carlo simulations are normally a little bit more complicated to set up compared to other approaches, but it's also not so important here. So here on the right side, you can see an example for 9 randomly injected faults. So we have the time interval, and here statistical calculated positions for occurrence of a time interval are used based on the derivation function. And here are the time points where the fault is injected. Because of only 9 runs, for sure, we only can reach a low accuracy. So normally when Monte Carlo requests a lot of simulation runs. Therefore, we ran also this example and made in Monte Carlo simulation with 1000 runs, but you can see results here. So we have again this time period between 2 time points, and here the time points where the faults are injected in the green lines define activated faults where the hazard could be prevented, and the red lines are defined faults injected which couldn't be prevented. So you can see there are two main time ranges where the hazard events could not prevent it. One what already defined in the beginning was when it's really early in the time period, can be also expected, but we have also at the end a time period which is because of averaging in the controller and based on the measure values, and also because of a duration of a signal transport when we come really short before the next time point, when it's too short to reach the safety mechanism, and so this also not prevent the hazard event. So now we can see that we have, as a result of this multicolor simulation, we have this diagnostic coverage of 85%. And now, in order to come back to the FMEDA, we will see we inserted here this 85%, what was our result, and based on that, the residual failure rate can be calculated. And at the end, because of a sum up of a complete item, we can also calculate an updated result of a single point failure matrix. So as a sum up, I could say, okay, the SystemC AMS is, because of a performance and also of a flexibility on different models of computation, usable for quantitative safety verification. I think it could also demonstrate that the dynamic fault injection approach is very efficient for this task. But we see also some points which could be more improved. For example, currently we defined our own interchange formats, for example, in order to define the fault descriptions, the matrix, but also the simulation of auto results in order to bring it for as an FMEDA input, and would be really helpful or sensible in order to bring it to a bigger context with different tool environments. If there is a standardized format or there are standardized formats available. And currently only we used our own libraries for fault injection statistic interfaces and so on. And this brings for people which will start with such kind of scenario, it's maybe more or less complicated to start. And for that, I'm at the end of my presentation. And if you need deeper information about the fault injection, please also contact me. But also, if you have additionally questions to that approach, what I demonstrated here. So then I have to say thank you very much.
Thank you, Thomas. Thank you very much for you and your presentation. We have some minutes, I think, or I would say we have some minutes for talking here. The reason I asked about this software is because you have this checking that things take a certain time. So I was just wondering if you have a very time accurate simulation in SystemC, or yeah, how time accurate is your SystemC simulation is perhaps the question.
Okay, we used here an algorithmical ECU model, so it is not cycle accurate in that case, but principle would be possible to integrate also in at least for the software parts and the controller parts, also to integrate in a cycle-accurate approach by integrating the instructional simulator. But nevertheless, the environment is not cycle-accurate. You're right at that point. But this reduces also the performance really extremely. So
Sure. And we have a question here from Christian. What is the requirement management tool Is it actually connected to the generation flow versus associated or manually referenced? Can you comment on that?
What kind? Can you repeat?
Christian, perhaps you can clarify.
So Thomas, on one of the slides, you mentioned that your fault injection flow starts with requirement from a requirement management tool. And I was wondering whether you have essentially a generation connection, so you can extract the data from the requirement management tool and automatically generate like your environment from this, or control the environment from this, or whether this is like more a manual transfer. You look at the requirement and then you implement like your...
No. We created an approach out of this requirement management tool. We create also a meta language description, and from a meta language we can create also the source code based on this description.
So requirement to meta is automated and meta to source code is automated. Both are generated.
Yeah.
Okay.
Yeah.
Good. Thank you. And maybe along the question of Ola, so it seems to me as if your abstraction is a signal, right? So you are using SystemC AMS, and most of the work you showed here seem to be injecting faults on SC signal or port, whatever it is, abstraction. So do you have any thoughts on on the abstraction level, on the proximity to the RTL? I can see how this works because it's relatively similar to the RTL structure, right? So the SC signals. Would you also be able to support other channels, maybe data types? So can you comment on this?
Yeah, sure. For example, the approach itself, so it is usable for the server, or for more or less for all of the models of computation. So it's independent from its TDF, pure SystemC, and also electrical networks. And it's a hierarchical approach which detects by itself or automatical what kind of model of computation is used. And also the data type, and based on that, and so-called low-level structures included automatically, and based on top of that, the defined fault model is set up. So we have several low-level structures for the different models of computations available. Is that what you want to know? Or?
Yes, this is a good answer. Yes, thank you.
We have a question from Martin. When you said that there were no standardized interchange formats, Martin says that he informs us that there is a functional safety working group in Accelera, which is looking into this. So are you aware of that group?
This is good to know. Maybe I'm not up to date in that. This could be definitely interesting for us.
I guess you will find it, of course, on the Accelera page, right? Here.
Yeah, sure.
Yeah, here we have it. Yes, and we had a raised hand from Anselm. Did you have a question?
No, that was pretty much answered. I was also wondering what was the requirement management tool and how it's connected to the flow. Thank you very much.
So if there are no other questions, thanks again to Thomas and your team. And please send in your slides so we can put them on the site.
Okay.
And then we ask the final speaker to start, and that would then be Per.